So let me recall some things which I wanted to recall for somebody, actually not here, but nevertheless I recall this. Okay. So recall the following, that we define if Xn this is a projective complex manifold, and here n, this is the dimension of X is n, and I assume that this is always that it will be connected. Recall that we gave a definition that X is special if we have the following property. For any P positive and for any L inside of omega P of X, so here, the P here is the same that here. L, this is rank 1, coherent, then for any L, then we have kappa of X and L, that this is strictly less than P. So we have this definition of special, and the term special comes, this is just to mean that this is in some sense opposite to general type. General type meaning that the canonical bundle has maximal Kodaira dimension. If you want, this is what happened when Kx is ample. So, and an alternative definition, so this is the simplest definition. So this definition, let me recall that this implies in particular, for example, that X has no surjective map onto a manifold of general type. This implies, but this is much stronger. This property is much stronger. And so, alternative definition 2, so this is definition 1. So, and definition 2, this means also that for any F, for some X, is if we have a dominant rational map onto some ZP, where P is positive here, what we have then the orbifold base, then Z and DF here, and so this is, let me call it the neat orbifold base. Neat orbifold base, then kappa of this is strictly less than P, which is the dimension of ZP here. So in another other words, this means that the orbifold base, this X never maps onto an orbifold, say, of a general type. So this is a more general, stronger condition. So we have this definition, and let me recall also that we had a first theorem for any X. There is a unique, in fact, a fibration here from C to some C, and this is the core map. Such that we have these two properties. First, the fibers XZ of C, so the general fibers C of C, are special, and 2, the orbifold base, we have C, and here this map DC, so this is the orbifold, the neat orbifold base of this, in fact, this is of a general type. So in some sense, so this core map, this means that you can split any X into a part which is special and a part which is of a general type. So if you want to, you can think of this in the case of surfaces. You can imagine, for example, that this kind of fibration, this is essentially what it says is the following. yes, for example, if kappa of x is minus infinity, in order to have something which is of general type here, so this is, x has to be P1 cross C and C hyperbolic, for example, maybe after a finite étale cover, or the x may be an elliptic vibration onto a curve of general type, for example. Otherwise, if you don't have this, this means that you are special. And we have given the classification of special surfaces. So yes, in dimension 1 for curves, special, this means either rational or elliptic. And here, you have both special and non-special when kappa is minus infinity and kappa is 1. So you have different possibilities in these two. But when kappa is 0, you are automatically special. And when kappa is 2, for surfaces, always general type, these are not special, never special. So you have this thing. And now this leads in a fairly natural way. And so we had a further decomposition theorem. And I will state it a little bit after. But before, let me give some conjectures, which are some conjectures about special manifolds. So special manifolds, they should be seen as higher dimensional generalizations of curves which are rational or elliptic. But pay attention that this is not given by the Kodaira dimension. The Kodaira dimension is not fine enough to distinguish things. So you may have, let me recall also that you may have special manifolds of dimension n and of arbitrary Kodaira dimension up to n minus 1, not the top one of curves, because this would be general type. So yes, special, I would like to say this is to mention that this is the opposite of general type, and general type, the term was introduced actually by Boris Moishezon. And so the conjectures are following. The first one, if X is special, then the fundamental group pi1 of X should be almost abelian. So this is the first thing in the topology, strong restriction. So this is the largest class probably where we can make this kind of thing. And this, I would like to mention that this property has been shown at the level of representations, linear representations of fundamental groups. So in other words, if X is special, it is true that for any representation in a linear group, the image is almost abelian. And now, for the hyperbolicity.
What is pi1 of x?
Pi1 of x, this is the fundamental group.
No,
A, B tilde, this is almost, the class of almost abelian fundamental groups. So groups with a finite index subgroup, which is abelian. Or if you want, a finite étale cover has an abelian fundamental group. H, so X is special if and only if. So this is the interesting thing, that this should be an equivalence. If and only if. Let me call first the Kobayashi pseudometric should vanish, but I will not define this. So these are, of course, conjecture. Another thing is that there exists some entire curve. So this is a holomorphic map from C to X with Zariski dance image. Zariski dance image, Zariski dance ZD image, or if you want, for any X, Y generic, in generic we have X, Y are chain connected by entire curves. Entire curves. So what is the meaning? If you take two generic points in X and Y, the expectation is that you can connect them, not as in the rationally connected case, by a chain of rational curves, but by chains of entire curves. And what are entire curves? These are just non-constant holomorphic maps from C to x. So this is the transcendental analog of rational connectedness. And if you take, for example, the easy case, an abelian variety is special. So this is easy. And then you certainly have this. You can even connect it directly by a straight line, in some sense. So you have this kind of property. And now, so this is the thing. And then you have an arithmetic analog for this. If you assume that x is defined over k, and this is a number field. This is a number field. Maybe this is not needed, but x is special if and only if x is potentially dense. And let me recall that potentially dense, this means that if you make a finite extension of your number field, then the set of rational points with values, if this means that x of k prime, this is Zariski dense for some k prime over k, which is a finite extension. A finite extension, this means an extension of finite degree. So this means that k prime is again a larger number field. For example, if you start with Q, you can take a quadratic extension or something similar. So this is this thing, and this essentially, one can say that this this depends on maybe essentially this or this statement. For example, if you take the case of curves, this is known. For n is 1, this is okay. This is okay, this is not complicated. For n is 2, this is almost known in some sense. The only exception for which this is not known, for the h is known. H is known, except maybe for the general Khafre surfaces, essentially. This hyperbolic, but for the arithmetics, then this is open in many more cases. There are some special cases, but this is quite complicated. And now, so this is what I wanted to say here for this. Yes, and now we had also Theorem 1, and so we have Theorem 2, which was assuming if we have an orbifold version of the CNM conjecture, this implies that actually the core map, which is C can be decomposed as an iteration of rational quotients, but in the orbifold world now. And J here, this is Ithaca vibration, but in the orbifold sense. And so I will not recall what it is, but this means essentially that X is special. I have forgotten maybe to give also the conjectures here. X special, this is equivalent to a tower of vibrations, orbifold vibrations, with orbifold fibers having either kappa plus is minus infinity or kappa is equal to 0. Kappa is equal to 0, and I will maybe briefly recall what it means. If we have xd, so this is a smooth orbifold here, as always, and we call it stage A Gj here, recall smooth and projective. So this means that the support of D is of simple normal crossings, and X being smooth, has kappa is 0 if, of course, if kappa of X and then Kx plus D is 0, but kappa plus is minus infinity if we have, for any f for X, which is a surjective vibration here, we have a need, and we have xd here, which gives actually a z, and here we have an orbifold base which depends not only on f but also on d, which is on x. And I gave briefly the definition, but I don't want to go into this kind of details. This means that kappa of z d f d here, this is minus infinity for any such f. So the thing is like this. And let me remember you that if you don't have any orbifold structure here, this property we can forget about, this zd here. The property of having kappa of z, recall, notice that we had this main conjecture which characterized, in principle, the unirootedness. MC implies then that kappa plus of x is minus infinity if and only if x is rationally connected. So we have the equivalence between this, in principle, when we have no d. But here, in the case where we have some d, we don't know this kind of relationship. We shall conjecture this and give precise statements a little bit after. So we have, or recall that we have this property. So in some sense, do you see? So this means that now we have a description, the structure of this special. This is actually a kind of a tower of things which are either rationally connected in some orbifold sense or with kappa is 0. And so now this permits to give, to reduce these conjectures, for example, to conjectures about the in the orbifold world now, but for these two kinds of orbifolds here. Huh? For the hyperbolicity conjecture, this is it depends on the version that you take. But if you take this one, for example, then this is true in dimension 2. True in dimension 2. This one, close. You have a certain, much stronger statement. Maybe I will give a statement which is true. The arithmetic thing is always much more complicated. So, yes. So, in fact, something, if you are special, and the only interesting case in which kappa is 0, so this is for K-free surfaces, these are very rational statements. For K-free surfaces, and for kappa is 1. For kappa is 1, this is true, strangely, but this is not true because you have the elliptic vibration, and then you can even show something which is more, that namely, if x is special with kappa is 1, for example, then you have almost a surjective map from C2 to your x, which implies, of course, a specialness, but this is much stronger, and then you have also the existence of this by taking a very large C curve inside of your C2. So you have a very strong version of this. Now for K-free surfaces, for the generic K-free surfaces, if they are elliptic, this is true. But if for the generic one does not know presently, but think of a case of Kummer surfaces, then this is obvious, for example. And in general, the thing which is here, this is obtained by approximating your Khafre by Kummer surfaces. And so then in the limit you get also this, for example. Yes. So we have now, we shall make, let me give another conjecture, which is the extension of this one, but using the core map conjecture. So if we have, assume that we take any x and we take its core map from x to c, and so we have C and this DC. So this is the orbital base, which is of general type. And so we have also a hyperbolicity conjecture in this case, which says the following: from any h from C to x, which is not constant because constant maps are not constant. Excuse me. But there exists W inside of C, which is different, and which is a projective. So this is a projective variety. So this is the conjecture, is the existence of this W. So for any h not constant, we have h of C is contained in W. So this is a very strong statement. So you have a certain algebraic, excuse me, this is not h of C, this is the composite. Sorry. And C composed with H of C, this is contained in W. So if you prefer, let me make a small drawing. So we have your X, you have your C here, and here you have a certain W. And so if you have any non-constant map from H to this, it has to be contained in the inverse image of W. So this is the statement, and if you want, assume, what does it mean? Why do we make this kind of conjecture? This is an orbifold version, this of Lang conjecture. Lang conjecture says that if X is of general type, then we have this property, we have in this case C is equal to X, and so you have a certain W which contains all the entire curves. So this is the strong version. The weaker version is Green-Griffiths conjecture, which says for any H, this is contained in some strict algebraic subset of X, if X is of a general type. But this algebraic subset possibly depending on H. The strong version is that you have something which doesn't depend on X. And in principle, this W, this should be the union of all the non-general type subvarieties inside of C, orbifold, and in this case, you have then, for any, you have this. And the arithmetic conjecture, if we have X which is defined over K, then this implies by the uniqueness of C that C is defined over K also. So this is easy. So this is defined over K, and in particular you have X of K maps by C inside of C of K. Okay, but this is not very interesting because in general this C may very well be a projective space. We had an example in which this is a projective space. So in order to have something of a general type, you have to take into account the multiple fibers here. And so this not, but we have something which is stronger. Yes, yes. Yes, then the conjecture, this is obvious, but what is very far from obvious is the following, that actually X of K prime for any k prime over k, which is a finite extension, we should have that x of k, c of x of k, intersected with x minus c minus w, with c minus w here should be finite. And so, what is the meaning? The meaning is the following. So the fibers here, these are special manifolds. So you may have very many rational points in the fibers. But what it says is that now, if you take this open part here, for any k prime over k here, you should have only finitely many fibers containing some rational point of over k prime. So you have a very strong finiteness result in this case. So this is the arithmetic statement. Also, this is inspired, of course, by Lang's conjectures. Now, let me give. So we have this thing, and now because of this decomposition theorem. Yes, and now this means that these conjectures here, essentially, these conjectures, they can be reduced to the orbifold, unfortunately, version of this one. Yes, so let me state the easier conjecture, not easier to prove, but it may be easier to state. So let us assume that xd, this is a smooth orbifold. Then, if kappa plus of xd is minus infinity, this implies then that xd is rationally connected. And so here there is a problem because we have to define what is rationally connected in the orbifold sense, and I will give the definition just right after. So we have this 2. If kappa of xd is 0, then this should imply now that, let me make the easiest statement. There exists some h from c to xd, which is, say, a morphism, and I will define what this means, such that the image of H is Zariski dance in X. So this, we have the exact statement, except that we have not defined what is a morphism. And we will define what is a morphism here. And now we have a general type case, 3. If kappa of xd, now this is n, which is the dimension of x, then for any h from c to xd, which is a morphism, kappa of xd implies that there exists w inside of x, which is different and which is projective. This is a projective, this is really subvariety. You have, for any such morphism, non-constant, we have h of c is contained in w. So you have this. So this is the conjecture for the non-hyperbolicity or for hyperbolicity. This is a hyperbolicity statement, and this is a non-hyperbolicity statement, and this is the strongest version of a non-hyperbolicity statement. And there are also, that I will not mention it, there exists also arithmetic analogues, but this is more complicated to state, plus arithmetic version. And I will go to this arithmetic version. What is what happened? I don't know if how does it work? Okay. Do you hear me like this? Is it okay if I speak like this? Yes? Yes, I don't, I think I don't know how to put this again. I'm not sure. Hold on. This should work like this. Oh. Thank you. Yes, so you have arithmetic version of this, and I will state this only in a very special case in dimension 1, where this is already open. So I just have here now to define what are these notions. In the orbifold case, so we have this. Arithmetic. Yes. So now we shall define what is a morphism. So here we take B. This is a smooth, connected, complex curve. Not necessarily algebraic or compact. The interesting case are the following. We are interesting P1 and C. And here even the unit disk is also interesting, but we shall only consider these two maps. And now let H, the definition. The definition is that we have H, C, B, excuse me. B to X is a dimorphism, say. Dimorphism, if we have, first, H of B is not contained in the support of D, and two, the condition is that for any J, D, this is sigma of 1 minus over Mj dj, as usual. So we have this. So these are the multiplicities here. And for any j, we have h, mj dot h minus 1 of dj. This is less than or equal to h star of dj. So, what is the meaning of this inequality? The meaning of the inequality is the following. The meaning of the inequality is the following. Each time, if we have a dj here, and so we have our curve B, and we have H, which maps B to this. Each time we meet dj at a certain point, then the order of contact of h of b with dj is greater than or equal to mj. So this is the meaning. The order of contact has to be sufficiently great in comparison with the multiplicity. So this is, and we have the classical version. Classical version. The classical version is the following: is that you have mj. I replace. You have the property 2 star maybe. Sorry, thank you. Yes, of course, this is not contained, not contained. And you replace 2 by 2 star, this mj, h minus 1 of dj, here divides h star of dj. And so the meaning is now that the order of contact is a multiple of mj. Any order of contact. Any order of contact. And so you have the difference between just this inequality and this, so to say, multiplicative inequality. So now we have these definitions, and I will denote by the holomorphic maps from B to X and D. This is the set of H which are morphisms, dimorphisms. Dimorphisms, and I will put all star of B and X and D. This is the set of H, which are this is it again. Which are classical. Classical morphisms. And so, so we have obvious implication. All star of B and X D, this is certainly included in all of B and X D, and this is certainly contained in all of B of X. Here if we forget any condition about D, and here this contains certainly whole, which is whole star actually of B, and here we take X and we take the support of D here. So this is the log version. This is the log version. What is the meaning in this case for the log version where the yes, here you see that if you have infinite multiplicity, if you are in the log situation, this means that this mj is infinite, so you can't have this. So this means that your map avoids actually dj. If the multiplicity mj is infinite, you have to avoid. So this corresponds to the fact that when you are in the logarithmic situation, so a reduced divisor d, or the coefficients are 1, so this means the multiplicities are infinite, then this means that you are in the projective quasi-projective case, which is just the complement, x minus d. So you have this kind of things, and this construction is functorial. In a sense which I not define, but you have to define more generally what are morphisms between these orbitals, these smooth orbitals, and this can be done. But why do we give this definition? Where does this definition come from? Now the definition is this. Let me make it in the simplest case where we have, for example, so we have an x, for example, which map onto a z, which is a curve. This is just slightly simple, for example. And what here, assume that we have two special fiber here over this point here, in which, and so this means that here we get here the infimum multiplicity for this. The multiplicity here is 2. So we have given to this point the multiplicity 2. And so now assume that we have a certain curve, which is here in that we have a map here from B to X first. And now we look at the composition with F. So we look at the curve F composite with H, and we would like to know what is the meaning of this, to interpret this in terms of the curve, and then this is very easy to see that your curve here, if you take it down, this curve, for example, which meets this, multiplicity free component, here in this point, if it meets it transversally, it will have contact of order 3 here in this point, because just you lift this divisor, and so you get a contact of order 3. But if your curve goes through here, you have just a contact of order 2 or a multiple either. So you have either a multiple of 3 or a multiple of 2. So in general, so what you get at the end is something, contact order, which is greater than or equal to 2. This is the only condition you can do. And so this is in order to make this functorial, so you have to decide this. And so this definition here is extremely natural if you want to this. If you had taken, on the other hand, the classical multiplicity, you would have gotten only 1 here, for example, and no condition. Yes, and so we have this property, and now I can make yes, give a definition. Yes, maybe this is better to do this. Yes, and so now the definition is that xd is, of course, the definition is obvious, is rationally connected if and only if, only if is easy, but the if definition is difficult, if we have kappa plus of xd is minus infinity. So this is, now that we have a definition of this R, excuse me, no, the definition is not this is the conjecture, sorry. The definition is xd if and only if any x, y generic can be connected by h. P1 goes to xd, which is a morphism. So you take this morphism, so this is the definition, and of course xd is uniruled. This is the same, this is just for any x. There exists an h P1 to xd through x, and so now we have this. Now the conjecture here is this, and you can add the conjecture actually that 0, that kappa of xd here is minus infinity if and only if X is uniruled. XD is uniruled. One has to pay attention, maybe, yes. Let me look a little bit at the Fano case, for example. So this is very wide open. Let me comment briefly. On this, yes, example. There is a small difficulty here, maybe. I prefer to restrict to the case where XD here is KLT. So this means that Nj is strictly less than plus infinity for any j, or the coefficient Cj is less than 1. So this is the thing, because in the purely logarithmic case, then you have some new phenomena, which are this. So, and so I think that, so we can assume in the case XD Fano, if minus Kx plus D, of course this is ample. And so let me give you some examples of what may happen. So let me take, I will take some examples. Yes, for example, assume that X is P2, and now D, this is 1 minus 1 over M times L1 plus L2 plus L3. So this is a very simple example, and so you can see, because you have only 3 things in P2 here, that this is Fano. This is Fano, KLT, for any M which is strictly less than plus infinity. And so now the thing is that this is very easy to get lots of elements in I have, yes. In a whole star even of B XD, B is P1, excuse me. B is P1. In the P1 case, this is KLT, just because you have the following map. You have a map from P2 to P2, so which maps X, Y, Z here to XM, YM, and ZM here. So this is a cover which ramifies exactly at order M over each of your 3 lines which are here. The P2 is D here. It ramifies at order M, and so this means now if you take any rational curve here in P2 through a generic point, say, then if you compose with this projection pi, so you get, if you get an H0, which goes from C or P1 to P2, and you project it, then you get immediately a D-morphism for this by projection, because now you have even a much stronger property, namely you have a divisibility property for the order of contact. So this is very easy to check. Now let us look at a slightly more difficult example. So we take again X is P2, but now I will consider D. This will be given by the following thing. We take 4 lines in a general position. And we take here multiplicities 2, 3, 7, and 41. And so you can make the computation that Kp2 plus delta plus D here, if you take minus, and this is all some of P2, and here you have something which is minus. This I have put here, this is plus 1 over, and here you have 2, 3, 7, and 41. So this is something of a very small order. And now I could show, for example, and so what you are looking for is for rational maps from P1 to things, and here you want to have order of contact. Each time you have a contact, at least 3, at least 2, at least 7, and at least 41 here. And so I can show that actually P2 is covered, is uniruled. P2D, this is uniruled. I didn't really seriously try to show that this is RC. This should be true. I think this is more difficult to show, uniruled, but uniruled already you need a certain argument. But what I don't know is with classically uniruled. Classically uniruled, this is more difficult because now what you want is to have the order of contact not only larger than 2, 3, and so on, but really very nicely distributed because you want them to be divisible by 3, by 2, by 7, and by 41. If you want to try to solve the exercise, would be very happy to have a solution. In this, I think this is true. There are some heuristic argument of counting dimension. This means how to say this? The number of parameters and the number of conditions. And so you get something which is positive. But the point is that you may have degenerations, and so this is not so clear. But really you can get something which is irreducible. You have a compactness property which is missing. So you have this kind of property. I think this is, and now close, an example which is close to this is the next one. Now we need a small definition. Definition 2 is here. We have that H C to X D. This is the entire curve. If it is if not constant, plus a dimorphism. And let me take a small other example, and now I take D prime here, and this is essentially, this looks like this one, but now instead of taking the multiplicities, I will take the multiplicity 2, 3, 7, and here 42, instead of 41. And so the things change abruptly, because now we have Kp2 plus D, this is OP2. So now we get something which is actually torsion. This is a torsion line bundle. Maybe you need to take 42 times this in order to get this, and so you get now something which is has certainly kappa equal to 0. And so the expectation is that for the entire curves, you should have lots of entire curves in this. And so let me notice that in this case, you can actually dominate your P2 by a singular Caffrey surface, and here you have a smooth Caffrey. And now you can produce, this is of course a cheating, one would like to have a direct production of these entire curves, but now, because this is a Caffrey surface, and so you have a result, an old result of Mukai-Mori, which tells you that you have lots of elliptic curves in your Caffrey, so this means that here you can always join actually any 2 points of S, by a chain of 2 elliptic curves. And so this means now that when you project these elliptic curves down, you get elliptic curves which are dimorphism, and if you compose this with the universal cover, then you get entire curves. D entire curves, and so you can connect any 2 points by this. So this is just a small example. So this is just this illustrates a little bit what is the meaning of this conjecture. And now I will go to the arithmetic version, but in a very simple case. Yeah. Apparently, very simple. So the situation is this. Now we will look at P1 now. X is P1, and we shall take D, which will be a divisor supported on 3 points with multiplicity 1 minus 1 over M0 dot, here I take 0, plus 1 minus 1 over M1. And here I take the divisor, which is just 1, the point 1, plus 1 minus 1 over M infinity, and here the point infinity. So this is a divisor supported on 3 points, 0, 1, and infinity. So you have actually the degree of kx plus d. Here, this is positive. If and only if, this is very easy to 1 plus 1 over m1 plus 1 over infinite is less than 1. Strictly less than 1. So you have this. Essentially, these are integers, m0, m1, m infinite, and so you have very few exceptions. This is greater than or equal to 1 if and only if you have, I don't remember exactly, you have 2, 3, 6, something like this, maybe, I don't know, 3, 3, 3, something like this, and maybe, yes. And you are in the Fano case, which is quite interesting. In the, this is essentially the Klein case. This one, this is Fano. This is Fano case. So you have a finite, very well understood finite number of cases, a small number of cases, which are these. And now now I will take the simplest example, which is K is equal to Q. And what are the, now we of course know exactly what are the rational points on P1, the rational in the sense of K is Q points. But now what are the rational points of the pair XD? And so I will explain what is meant by this. What are the rational points? I will have two versions. In fact, I will define things which will be P1 of D, of Q. So this will be the non-classical rational points, and P1 of D star, which will be the classical version. And I will explain you what is the idea, and the idea is very close to is essentially the same, actually, that for the mapping curves to the orbifold and having certain order of contacts. And so the idea, this is very nice. I find it's not due to me. In fact, you have this kind of thing. And so what you are looking, in this case, so you have P1, and so what you replace your base, actually you have a function field version over a curve, which is a more geometric version. This is an exact analog of this, but I go directly, because of lack of time, to the arithmetic case, and here I have a spec of Z. Spec of Z, this means that here we have maybe 2, prime 2, prime 3, P is 5, and so on, and here you have a certain general P. And so here, what you are looking, you make a fibration of this, and the fiber here, this is each time, the fiber, here this will be P1 of Z2. So this is the field of degree of with two elements, and so you put here P1 of Z3. So you take just the reduction modulo P of your fiber. And now you have 3 sections, which are 0, 1, and infinity with certain multiplicities, m1, m2, and m infinity, which is here. So you have this section. So these are the points. You take just the reduction of these points. So this gives you section. And now if you take an element x, which is a over b, which belongs to q, here, and where I will assume to simplify that there is no but this is not interesting, but b is not 0, so I exclude these 2 points, 0 and infinity, and I assume, of course, that a, b are coprime here. So these are integers belonging to z. And now this x, again, can be seen as a section, because for over xp, I will take xp, which is the reduction of x mod p. Mod p. So this will land in this. So you have here a section, and so this section. Let me explain. This section x. Let me maybe call it this. The section is x. We have section 0, section 1, and section infinity. So I have that x meets 0 at p if and only if we have a, if and only if p divides a. So you have a divisibility because the reduction will go to 0. So this means that we have this divisibility. Now we have x meets here 1 at p is a prime here, if and only if we have p divides a minus b. And we have also x meets infinity, the section infinity at p, if and only if p divides b. So we know what is the meaning that this section, which we think of a curve, meets each of these sections. But we want also to have a contact order. And so the contact order is defined in the following way. Now, the order of contact. The order of contact let me maybe call the x 0 at p. This is just the exponent. I'm assuming here that that p divides a, the order of exponent of p in the prime decomposition. Decomposition of a. A is the numerator here. So we can define what is this order of contact. So the idea is really, if you are in the function field version, this corresponds really exactly to the thing of an order of contact in the geometric sense. So you have this, the order of contact here, we have x infinity of p, this is the same thing, but the decomposition of b here, and here, the x1 at p, this is the same thing, but here you take a minus b. And so now we are in position to give the definition. Now I will just define P1, D of Q. This is the set of X, which is equal to A over B, such that, such that Xi P is greater than or equal to Mi, and for any I which is equal to 0, 1, or infinity. Is it understandable? So you have a certain order of contact. Here, order of contact, so you have a certain order of contact which is here. And so you want to have this order of contact for all of these three sections. So now what you have, and so I have also the classical definition, P1 of D star of Q. I just copy the definition which is here, but in this arithmetic version. This is the say of X is A, B, such that we have Xi, P is divisible by Mi for any I which is equal to 0, 1, and infinity. So this is very nice. Let us try to understand what it means in the simple arithmetic terms. What does it mean? You will see that one has a very simple interpretation, at least for the first one, for the classical. So what is the meaning? So this means, here, in this situation, this means the following. This means that A actually, so I'm here in this situation. This means actually, look, this xi, I put I is 0. So this means that xi is divisible by mi. This means that A is of the form alpha to m0. For alpha, some alpha belonging to Z. I take maybe the absolute value. So do you agree with this? Do you see why this is here? Because the condition which is here, I take I is equal to 0. So this means that for any prime which appears in the decomposition of A, the exponent is divisible by mi. But this means exactly that I is an m0th power. Okay? No? No. That's easy. So, for some of this form, now we have a B, this is alpha power m infinity. For not the same, of course. This is some beta. For some beta, there exists beta in Z such that this is exact m infinite power. And here we have C, which is A minus B, which should be a gamma to the power m1. And so there exists gamma belonging to Z. So you have this property. In other words, for the classical points, you are just trying to solve the equation alpha m0 minus beta m1 is equal, plus, or maybe you can put signs, is gamma of m infinity. For example, so you are just trying to solve this equation. Now, if you are in the non-classical situation, what will happen for P1D, yes, of Q? What is this? Now we are replacing the condition here that all exponents are divisible by mi by the condition that all exponents are at least mi. And so the condition, this has a names in arithmetic. Let me say that A is, say, K full. Maybe I will take a D, for example. This is a D belonging to Z plus, maybe, to just. Is K full if, the radical of D, this is just the power of, this is just the product of all primes dividing D. This is the product of all these primes if radical of D to the power K divides A. So this is exactly this thing. So this is K full. There is K full, and here this is the set of X equal to A modulo B, such that we have A, this is M0 full, B is M infinity full, and we have C, or A minus B, this is M1 full. And now We don't have such a nice equation, algebraic equation for the solutions. So the situation is a little bit more complicated. I would like to mention one thing. If you fix K here, and if you take D, the asymptotic number of K full numbers which are less than a certain bound. If you take the exact powers, this will be this bound divided by 1 to the power 1 over K. But here, you don't have much more, you have a certain, asymptotically, this is a certain constant, positive constant, times b power 1 over k. So this grows likely to the same. But nevertheless, and so now let me state what is the conjecture. The former conjecture now takes the form in this very special form, case, and the conjecture the arithmetic conjecture, in this case, this can be said very easily. The conjecture is that P1, this is the orbifold, I call it orbifold model. Model conjecture, we have P1 D of Q. You can replace it by number field, but this is more complicated to state. This is finite if and only if we have P1 D is of a general type, which means Kp1 plus D, the degree of Kp1 is positive, or this is equivalent to the say that M0 plus 1 over M1 plus over M infinite is less than 1. So you should have a finite number of solutions when you have this inequality. And so I would like to mention also that we have the following inclusion. P1 of D, star of Q, this is included in P1 D of Q. This is very clear because here you have exact powers and here you have full numbers. So you have this. Now, this part is proved. So we have the finiteness when you have a general type condition. So you have the finiteness of this, which of course does not imply finiteness of this. But this is here, this is open. This is open. This is proved, this is essentially Faltings plus epsilon. The idea is in fact very simple. This was noticed by Darmon Granville independently. And so if you have this kind of object here, what you can make is just to make an orbifold étale cover of P1 over these three numbers, which with ramification orders, which are exactly the ones given, which one M0 over 0, M1 here, and M0 here. So you have a cover which will be of general type necessarily. And so the point is that now the points, the classical points which are here, because they are classical precisely, they lift essentially to the étale cover. So you in Faltings implies finiteness. You may need an extension of a base field, but it's not so serious. And so you have this, and so this means that actually you have finiteness by Faltings. Now for this is completely open because you don't have. The thing is that these points here, they don't lift to finite extension field, so you can't conclude of this, but nevertheless, the ABC conjecture implies this thing. This is fairly easy to show. If you have ABC, you have this. But nevertheless, this is open, so this lies between something which is proved and something which is completely. But in my opinion, I must say that this is geometrically very obvious, while the ABC conjecture on the geometric side is not so obvious to me, at least. And so you have this kind of thing. And now I would like to finish with a small observation. So let me give a small definition. So we have X, this is projective smooth, is, say, weakly special if for any x prime to x, which is a finite unramified cover, there exists no map to some z which is of general type and with p positive here. So this means that the condition is that for any no finite étale cover, you have a map onto something of general type. And so what we know, so this means that actually no finite étale cover of X is very weakly special. So this is a stronger condition. And so we have seen that in the surface case, we might have something which is very weakly, which is not very weakly special, case of surface. So we had a surface here which was very weakly special, but not very weakly special. So this is a stronger condition than weakly special. Of course, if pi 1 of x is 1, then weakly special is equivalent to very weakly special. Weakly special, and in general, so we have seen also that special implies weakly special. So the question is this, and actually for surfaces we have equivalence between these two things, but in dimension n, when n is greater to 3, we don't have, this is not true. I shall briefly say this, we have not. And now we have two conjectures which are conflicting. I introduce this just because of these conjectures here. So we have a conjecture. This is by Abramovich, Collio, Telen here, and this is actually taken again by Harris and Schinkel. And so what they say, that they don't use this property. If X is defined over another field, okay, then X weakly special should be equivalent to X is potentially dense. Potentially dense. And on the other hand, I have a different conjecture. So the conjecture prime, which I said before, if I have X over K, then X is special, this should be equivalent to X is potentially dense. And so this, if you have an example of a manifold which is, so you know that this here, so which is weakly special but not special, then you have a conflict because one conjecture says to you that this is potentially dense, and the other conjecture says that it is not. So you have a conflict between these two things. And the point is that when there exists X3, dimension 3, projective, and so on, which is defined even over Q, so that X has some of the following properties. Pi1 of X is 1. X is weakly special, but X is not weakly special. So we have this property. So this means that we have a conflict in this between these two conjectures for this special manifold. So the arithmetic, the theory of arithmetics in the present days is not strong enough to decide between these two things. But now, if we take the hyperbolic analog of this, now that it is possible to show the following on the hyperbolic, for the hyperbolic version. It is possible to construct such examples here in this situation, so let me briefly give, so you have here for this X3 they look like this. So you have the J, which is an elliptic vibration. We have an elliptic vibration. We have kappa of X3. In fact, this is 2. Kappa of S, for example. This can be chosen minus infinity. 0, 1. So you have this, but we have, this is the core map. But we have S and D, J here, but kappa of S and dj, this is equal to 2. So essentially this implies that this is weakly special. This is fairly easy to see with a pi1 is equal to 1 here. So this looks like this. And now there are certain examples now on the hyperbolic case in such a way that now the Kobayashi pseudometric d of x, this is just J star of a certain metric delta on S, and this is a real metric. This is a real metric, which is, this is really positive. And so what does it mean? This means the following. This means that if you take any map H from C to X3 here, a non-constant map, for example, then the image here has to be 1 point. So all the maps here go to 1 point. So this means that the orbital base is actually really hyperbolic in this case. And so if you think of the Lang's conjecture and the analogy between arithmetics and hyperbolicity by Lang's, this means actually that this should also not be compatible with potential density. This would mean, for example, that actually the rational points here on this, they have to map to finitely many here in S. And so this is, of course, very far from potential density. And so I will stop here.